actually has to be studied as much, if not more than, the individual parts. So it's one thing to go in there and do analysis, structural analysis, part by part by part, do CFD analysis, piece by piece, part by part, topology optimization kind of part by part. But just because you've kind of done all of that, does that guarantee that you've got a good assembly, a good product? It doesn't. What you need to do is look at studying and analyzing the overall product. Okay? And so the presentation, discussion early on in the semester is so that we can kind of end by doing system level analyses. We want to do finite element on the system. We'll do it on the parts, but we want to be able to do it on the system. We want to do CFD on the system, not just on individual parts. Okay, so that's kind of the move the assembly modeling right up at the beginning of the semester. Assembly modeling, collection of independent parts with assembly dependencies. So what are the dependencies? There's two types. One of the dependencies is referred to as kind of hierarchical, where it is kind of father to son or parent to child. Okay? So being able to understand this part is connected to this parent part. This parent part is actually connected to another parent, and so the relationship from part to part is referred to as the hierarchy, and it leads to an assembly tree. The other thing that we need to focus on, the dependencies, are the mating conditions. How does this part interface with another part? So one is kind of the genealogy, the other one is really referring to kind of the relationship, the distances, the face-to-face contact, the axis-to-axis alignment conditions. So what is the hierarchy? Well, it leads to an assembly tree, something like this. This is an example straight out of your textbook. So there's a good discussion in there about kind of the hierarchy of assemblies. It's pretty obvious that at the lowest point on any assembly tree, you're going to have individual parts. Those parts are then collected into an assembly, generally referred to as a sub-assembly. And those sub-assemblies may be collected with other parts into other sub-assemblies and eventually to the overall master assembly. In this class, not recently, but it wasn't too uncommon to see an assembly that had 500 parts in it, no sub-assemblies. So it was a master assembly, 500 parts. Not a very good assembly tree structure. Okay? In fact, when you think back to for the BYU students, when you think back to 172, if you did 172 kind of under me, we get a little discussion about assemblies and building them up. But the last air engine project that is done in 172 oftentimes is a very flat assembly file. It's all parts connected into a master assembly, and that's not what we're looking for out of this class. We want to see a very elegant, a very appropriate assembly tree structure in this class. And so you need to be thinking about, how do I design this assembly of parts? The mating condition.
Will we be turning in something like in a hierarchical tree, assembly hierarchical tree?
So in the past few semesters, part of the presentation is where the students kind of talk openly about, here's how we organized our assembly, and this is what our tree structure looks like, and we have this sub-assembly that is the front suspension, and we have this assembly which represents the motor and the electrical components and everything else. And so that is usually folded into the final presentation.
Okay.
But definitely you want to have a strategy that you're working on.
Right.
The mating conditions refer primarily to how is one part, its origin, okay, its absolute 0, 0 point. How does that absolute 0, 0 point map to the 0 point of the assembly, the subassembly, or how does it map to the master assembly? What is the space and what is the orientation? So what is the distance that it's separated and what is the orientation of its x-axis in comparison to the x-axis of its subassembly or assembly? And so this is intended to kind of trigger in your mind, I should be setting up some kind of a spreadsheet, and the spreadsheet needs to hold kind of this understanding of this part is related to this part by this offset and this orientation. And that way when you go to actually build, set down and build your master assembly top down, you don't have to sit there and kind of rethink everything because you've mapped it out prior to going in and trying to model it. So for just a minute, we're going to take a sidestep into the shipbuilding world. And this is a drawing that I've had for probably 40 years. You can go online and you can find actual drawings for all kinds of sailing ships and boats if you want to rebuild them either as a scale version or as a full-up Noah's Ark kind of thing. When you go and get those drawings and purchase them and bring them down and start looking at them, you'll find out that in the shipbuilding industry, they have a global coordinate system that is laid out based on water lines, butt lines, and station lines. And so the water lines happen to be all of these horizontal lines that's in this right side view. All of these horizontal lines are what are referred to as water lines. Station lines are the things that run from the tip of the ship all the way down. These are station lines. And the butt lines are the things that go from the center of the ship outward. And so by using those, that kind of XYZ reference, they can specify any point on the ship. A bulkhead on the ship is at a station line. Okay? And so they can easily kind of lay this out in a global coordinate system that everybody understands. They say, you go to this station line and to this water line, and you cut a hole and you put a gun port in the ship. Okay? And they can go exactly to that. In olden days, they did it as a craftsman. In today's world, if you were working for a shipbuilding industry, they use the exact same kind of coordinate system, and you go in the digital space to that station line, that water line, that butt line, and you do your modeling in that space. By doing that, by using this global coordinate system, they not get connected up.
One said they can't hear, but they're not supposed to be able to hear with this, but I'm just going to type them a message.
Okay. Don't watch her. So in today's world, it's very easy, if you're a single part modeler on a ship, it's very easy for you to open up a new file, for you to go to that XYZ location, that water line, butt line, station line, and you begin creating a part, and you save the part off. The person in the master assembly, when he wants your part, what does he do? He says, go and get this part, import this part, and it's going to prompt for what? Where do you want it placed? You want to shift it? You want to adjust it? You want to do anything to it? And what's the answer? No, don't do anything to it, just bring it in, because it'll drop in to the exact location, the exact orientation that it should have based on these planes. So these are actual planes and locations that are mapped out and established well before any ship modeling ever happens. The exact same thing is, click down arrow. We need to go to the next slide. Oops, too many downs. The exact same kind of global coordinate system is in the aerospace industry. Okay? So if you look at this, they have water lines that run from the ground up. Okay? They have station lines that run the length of the airplane, and then they have butt lines. Hopefully the remote students can hear now. We brought our Tandberg back online, and I believe we're reconnected. So the question, if we have a global coordinate system for the shipbuilding industry, we have a global coordinate system for the airplane industry, is there an established global coordinate system for the automotive industry? There's not, that I've seen. Okay? It doesn't exist. It should, and some companies try to implement a global coordinate system, but most of them say, well, a car can fit in kind of a shoebox, a large shoebox. But because it's, a reasonable size, they don't have to think about, a ship being a football field in length, or a plane.
Department of Education.
I have no idea.
I really hope they can.
That's got to be
Why is it?
Oh, wow. It's switched over to how did that
That's one of the
Don't use the mouse on that other.
Yeah.
Not free. So many of the automotive companies are attempting to implement some kind of global coordinate frame. You will see at some companies they say, well, we need to locate a point right at the nose of the bumper. And it needs to be at the right height. It needs to be at the axle of the front wheels. And it needs to be on the center line of the car. And so you'll see that they have attempted to try and find a global 0 point that everybody can reference off of. But again, because they, in their minds, say, well, a car is not that large, they have not really pushed forward in defining a global coordinate space. And so it's really company by company by company. What I would recommend to each of you as you sit down and figure out your strategy for modeling this car is that you as a team decide where your global origin is going to be located, and from that you then develop planes and axes and points that will be the basis for your skeletal assembly model. Okay? I think we're back to presentation. Okay, so planning the assembly. Identify the dependencies between the components of an assembly. This will lead to either a bottom-up or top-down approach or some kind of a hybrid. Okay? Identify the reuse of components and subassemblies. And so really study, can I get away with my front suspension being used for all suspensions?